Hello, hello. So, as you know, I'm passing back exams in a moment. A couple of you I'd like to talk to, so I've either contacted you or if you took it at the testing center, I will email you up with that. But I have a couple that I'd like to call. If you're here, you have a chance at getting a few points back for a multiple choice question you just didn't answer. And I figured maybe like to take a minute, see if you can answer that real quick. Have a chance at some points. So apologize if that's embarrassing to call you out. Can happen to anybody, but I just like to give you the chance to come up and answer that. And then I'll be passing back the remainder of the exam. So it'll take a few minutes. I'll get them passed out. My plan right now is to go over the solutions tomorrow at 10 a.m. online, not here, 10 a.m. Okay, so tuned in to that if you'd like. If you'd like to wait till Thanksgiving break or when you need to fall asleep or something, feel free, whatever you'd like. So that's the plan. I'll send an email to kind of remind you of that as well. All right, but that'll be tomorrow. Okay, so I'm going to take a few minutes, get these sorted out. So is Leslie Castaneda, you here? Haley Pittenger? Come on up. The first three, maybe four here. That's not. Yes. You have a chance to answer that. Just go ahead and Gino Bonilla? Come on up. Wicked is already out. I've been saving all my friends with cars to maybe no one's one other thing before I get going, a few people. So I've done my very best to make it fair, and I'm gonna take just a second to score these and update as needed. Leslie. Camille Sewell. Trent McKinney. Xander Hugh. John Levesque. Ben Vanderberg. Emily Newell. Tracy Fournier.
No, we're not.
Jonathan Harkin. Ethan Moon. Natalie Johnson. Patrick Daly. Tyler Nemeth. Gabrielle Yusuf. Gordon Meeks. Dylan Cook. Anthony Glenn. Captain Hall. Ethan McDevitt. Gracie Day. Sarah Christopher. There's two in this. London Levine. Colby Rapp. Aubrey Odell. Max Torelba. Garrett Grayson. Merritt Picora. Jeffrey Secocas. Ricardo Silva. Jason Simmons. Emma Potter. Layla Hampton. Taylor Miller.
I watched it. Yeah.
Oh, you mean like the song? Oh, you mean like their rendition, or the song? I know the song's like something second half.
I have
Some
heard
of the
that.
favorite ones are I love No Good Deeds. I love No Good Deeds. It's one of my favorites. And then the I'm Not That Girl remix. And then they Stephen Schwartz had two songs. He wrote them for this.
Long Trent. Ethan Glenn. Adam Scott. Jacob Ciselski. Haley Foster. Luke Aguilar. Paul Manasco. Mason Trumbull. John Taylor. Bryson Williams. Guy Sam. Jacob Reinhardt. Brooke. Annie Penn. Faith Stanley. All right. So normally I will have would have posted your grades. I will do that. I've got it all in the Excel file. Got the updates that I just made at the beginning of the class. I also have exam ones that have not been picked up. So if at the end of the class you're interested in coming by to grab that, feel free to come by. And I realize I've been in a rush today. I forgot my water. So hopefully I'll be fine. Might swing by the water fountain in a little bit. But let's get back to BOD. All right, and there will be plenty of availability for questions online. If you haven't used it, you can just use YouTube chat, and I'll see it pop up pretty much right away. I was collecting some questions on our last lecture from somebody who couldn't attend in person. So feel free to use that. You don't need to use your real name. In fact, I'd encourage you not to because this gets placed online. So it's your prerogative to.
Sorry, did I miss my name?
What's your name?
Adam.
Yeah. Let me get that for you. Is this correct? Okay. All right. Just because that's getting published online, if you don't want your name asking questions, that's up to you. I'm supposed to not do that without your permission. So if you use your real name as your YouTube sign-in, whatever, then be warned. That's your prerogative. If it's a serious question, even if it's some rando on the internet, I'm going to answer it as if it's a serious question and it's one of you. I don't discern or discriminate that way. Yeah.
Do you remember that time that random guy joined your live and started asking those questions if he was like a junior in high school and stuff?
Yes. That was the last semester, right? In the spring. Yeah, so sometimes random people will show up, and if it's a question that's relevant and I think we might learn from it, I'll answer it. So if you decide to terrorize me in the future because you hated my class, then just hop in my YouTube and make me boot you from the stream. Okay, just kidding. Okay, I will. Speaking of, I have a question. I will post these grades probably later today, maybe tomorrow, so that you'll have it at least by the time we're doing the exam review session. Normally I would have posted it before, but I just didn't quite get to it. So I have all the grades in my grade book. I just need to upload that to Moodle. So for those of you who are here and picked up your exam, you'll have it. If not, it'll be by tomorrow. Okay. Any other questions? Mostly the questions will be tomorrow for the actual exam recap. And you're also welcome to email me. Maybe you watch it later so you're not live questioning. That's up to you. Okay, so last time we talked about biological oxygen demand, what happens when we send it downstream. We began thinking about it in terms of tracking what's happening as we flow downstream. We looked at the dissolved oxygen, what we might call a sag curve, where it gets depressed for some time before returning back up. And we could then describe that as an oxygen deficit, which in a way, I didn't draw this last time, but we could draw a deficit as an increasing deficit for some time, and then the deficit will go back down. This would be the dissolved oxygen deficit. We're going to describe that as just D, by the way. So if the blue line here is our BOD, the microbe food, well, what's going to happen to the oxygen in solution is we'll have some saturation value. Bless you. And then we could imagine we'll be up close to the saturation value, and then it will dip and hit a low mark and then kind of come back up. And so the deficit is just the difference here. I'm not drawing it exactly to scale, but I kind of tried to make it close, right? So you could look at the deficit in two ways. One is kind of just the difference here between this line and the current spot. That'd be the deficit at any given point. And we could potentially plot that as a value that increases up until the deficit is at a maximum and then starts decreasing again as reaeration happens. So a few ways to look at that. We talked a fair bit about that already. This would be the DO, whatever the current dissolved oxygen level would be. And so that's kind of a useful way to look at the scope of what happens in a stream or a river when we discharge biodegradable organics, wastewater stuff. Okay, so we talked a little bit about how to measure it. Here was a slide where we kind of went a little deeper on the DO. And then we began to talk about how do we model the amount of BOD that is still there. And this is going to be kind of an odd thing to describe because the amount that is still there is really, it's oxygen-demanding substances that have not demanded oxygen yet. It's just a weird way to phrase it. So we can think of it as there's some ultimate amount, some initial amount. If we gave it an infinite amount of time, how much oxygen would be demanded by this food? How much food demands oxygen in our water? And we could say that at some time t, there is LT remaining, BOD, plus whatever has been demanded up to that time, as we talked about that. L naught would be the infinite BOD, kind of the starting point, and LT would be after some time, how much is remaining if at that point we gave it an infinite amount of time. So we could say that's L naught would be, let's say, L at day 5 plus BOD that has already been demanded at day 5. Okay, it's one way we could describe it. We want to do this so that we can have a handle on the actual amount of BOD that corresponds to what's happening with our dissolved oxygen sag curve and what's happening with ultimately the stream and the biology altogether. So we can look at this L as a first order rate equation where biological activity is removing it. Okay, so removing it with some rate constant K. This would be our BOD reaction rate constant in some per time units. And then that's going to be rather straightforward. We're going to keep 2 rivers and streams for this type of analysis, so we can look at some time in a plug flow like system in a stream or a river. If I said lake, I didn't mean to. We're going to keep it to streams and rivers. And that will give us some way to look at how our waste is changing as it flows. So with that, we want to know, how do we balance oxygen versus this oxygen removing action by the BOD? And that's going to be this deoxygenation balanced against the re-aeration. So aeration meaning we're bubbling or somehow mixing oxygen with our water. And deoxygenation would be that rate at which the microbes are removing oxygen from the water. So we'll have KD for the deoxygenation rate constant. That's essentially going to be the same K here. So that's our KD. And RD would then be a rate of deoxygenation. We could describe that, just like we were a moment ago, as KD times L naught times e to the minus KDT. So we're just connecting the dots here. That would be our rate at which we're removing oxygen from the water. Okay, so then our re-aeration process is going to largely be a physical process. There's a few chemistry things, the equilibrium constants, maybe temperature dependence, some other solutes that might have an impact. But overall, it's a physical process that's bringing oxygen back into water, is probably the best way to look at it. This is going to be proportional to how much oxygen is missing. So it's proportional to the oxygen deficit, D, we talked about a moment ago. So the amount missing is a driving force. There's a gradient, and the atmosphere is going to be pushing oxygen back into our water because it would rather be at equilibrium with the water than be far away from equilibrium. So if it's close to equilibrium, that driving force is small. If we're far from equilibrium, it's a stronger driving force pushing oxygen into the water. Now, if I, let's say, took a straw or took the cap off my pen and filled it with water, there's a small little spot there in a straw or a water-filled pen or something that is able to mix with air. A fair bit of volume here, but only a little bit that could mix with air. So we can see just the physics of that means there's not much exchange happening. And that would be very different if I then took that same amount of water and sprayed it up into the air in little droplets. The same amount of water would end up getting a lot more air, a lot more oxygen into it if we sprayed it out as little droplets because of how much contact with the atmosphere there would be. So in the same way, we have physical processes or physical dynamics of our rivers or streams that make a big difference for re-aerating our water. This is also why, especially here in Louisiana, you'll see many ponds have big fountains that are spraying water. It's pretty, yes, but it's also providing a lot of re-aeration. A lot more so than would just be happening if it was just calm water there. Okay, so Kr then we could describe as our re-aeration rate constant. And we could make that proportional to the rate constant and the oxygen deficit. So there's a question then of what is this Kr and how do we get it? And what is exactly our definition of the deficit? I already mentioned this and drew it on the graph, but a clean way to describe it mathematically would be the DO at saturation. So S for saturation minus the dissolved oxygen at that given time. So DOS minus DOT. Okay, then the Kr value is mentioning this is related to the physics of what's going on with our stream or river. And this is something that we've found empirically, meaning we studied it and we've measured it in practice, and we got some empirical, some data-driven way to give a number. This is not a theoretically derived equation. This is just from observations. It turns out that we can say if we have some speed of the river and some depth of the river, we can make a good guess at this re-aeration rate constant. If it's really shallow, that's relatively speaking a lot of water in contact with the air. If it's really, really deep, well, the stuff down towards the bottom has no contact. So it's like almost nothing's going to be exchanging. If it's moving fast, that's going to tend to be more turbulent, more exposure, perhaps rapids, things like that. So if you have a shallow depth and a high speed, you'll probably have rapids. Okay, higher mixing, higher reaeration. So the equation goes like this. It's 3.9 times the speed, u, to the 1/2 power divided by the depth, h, to the 3/2 power. It's just what it is, and that's just what we're going to use. So that's our reaeration rate constant. So if we know something about the speed and the depth of the river, then we know something about how well it's going to reaerate. Okay? Not a whole lot else to say other than, you know, someone got to play in a creek for a while to figure that out. All right. So let's take a look. A quick thought here, and I mentioned this a moment ago. That K, is that K really KD, or what is the difference? So the rate of deoxygenation at any point in the river is assumed to be proportional to the rate at which we are removing the BOD. So the rate of deoxygenation would be proportional to KDLT. But we are going to distinguish, and I think I misspoke earlier, which is why I have the slide to remind me to correct myself. The deoxygenation rate constant KD is often assumed to be the same, once temperature adjusted, to the BOD rate constant that we find in a standard BOD test. For deep, slow-moving rivers, that seems to be reasonable, but if we have a lot of reaeration, it's less valid. So we can't always say exactly that. So we're going to keep those separate. I know I mentioned earlier when we were here, I kind of mentioned this K being the same as this KD. So I apologize, that's actually technically incorrect. Sometimes it's correct, sometimes it's not. So just keep this equation you'll have, I believe, on your equation sheet. So just keep that in mind, that a rate of deoxygenation will be related to that, but could be separate. All right. Here's a few typical water bodies. What are their KRs, just as a reference point? So this is KR that we were describing. So if we have a small pond or backwater, this reaeration rate constant somewhere between 0.1 to 0.23 per day is the rate constant. Compare that to, let's say, a sluggish stream or a large lake, 0.23 to 0.35, going all the way up to rapids and waterfalls being larger than 1.15 per day as the units. So if we put that into some calculation, we would be able to see, okay, well, what is that doing to the oxygen? We could even perhaps make some plot and do some graphing about what that looks like. Might be fun use of MATLAB or something. I'm not going to make you do that. All right, but what I would like to do is take a look at specifically how do we determine something about the critical point where we have the most impact, or the most important impact, which is the time when we reach the highest deficit, or rather the lowest oxygen, the dissolved oxygen amount. So those are going to be our key moments that we are really concerned about and want to design our treatment to make sure that that key moment is not so bad that it's causing a fish kill or otherwise harming our environment. Because if we can discharge just a small amount of BOD and nothing bad happens to the environment, okay, that's probably what we want to be doing. Probably doesn't make sense to try to get rid of 100% of the BOD, but it also doesn't make sense to kill everything. All right, so putting all these curves together here, what we'll notice, if we draw it better than I did earlier, we can identify a critical point. As BOD is dropping through here, our rate of reaeration is going to start increasing because we're getting some oxygen deficit. So we will have some increasing reaeration rate up to a point, that's going to cap out when our oxygen deficit as it is at its maximum. So if we look at our dissolved oxygen here, the lowest point, this is the largest deficit, D. That's going to be the moment where our reaeration is happening the fastest, and we can then learn something about the whole system. We can also identify this critical time point, so TC, or this critical distance. If we're discharging here, how many miles downstream does this happen? What town or place, area is affected could be quite important, especially if we were going to try to figure out something about who's causing the problem when we find a patch of the stream that's has degraded water quality. Okay, so to get there, to be able to model this, we want to take a look at some equations. So to model the oxygen deficit, we could start with dD dt, so the rate at which the deficit is changing. This is going to be equal to the rate at which we have deoxygenation minus the aeration. So this is going to feel a little upside down because we're talking about the deficit, the lack of something. As that changes, to track its change, we have to say the deoxygenation rate minus the reaeration rate. Okay, so if we take those two rates we described earlier, they are Kd times L naught times e to the minus Kt. That's our deoxygenation rate, minus the reaeration rate, which is a little simpler, Krd. All right, so take a moment and integrate that. Yeah. Yes, that should also be Kd, sorry. And I'm just kidding, by the way, this is a tough integral. We're not going to do that. We're not even going to bother with that. Fortunately, the book does that and gives us an answer. And as we'll see, probably this is something you could do if you go back to calculus and kind of scheme about all of that. But we're just going to take the book at its word and say, here, the deficit equation will end up coming out to be Kd times L naught divided by Kr minus Kd times e to the minus Kdt, and you'll see that correction comes in there, minus e to the minus Krt, all that plus some initial condition of d naught times e to the minus Krt. Okay, so we have this big equation, and I'm going to give you this on the formula sheet, so you'll have this. What this tells us is that if we know something about the time that we're interested in downstream and some of the initial conditions and the rates, we can solve for the deficit at any given point. Okay? So this is actually not too different than setting up, let's say, a plug flow reactor with a rate in it. This just happened to be two rates, and we integrated just like we would in a mass balance. And we just had a few extra, not variables, but a few extra constants that are just going to float around there and play a part. So this gives us a pretty good equation to deal with, but there is one problem. If we take a look at this, the beginning of the equation has this term. If we happen to have a situation where the rate constants for Kr and Kd are the same, we're dividing by 0. So we get into trouble. And it's probably going to be rare, but that could happen, right? So we had Kd times L naught over Kr minus Kd. So there is a moment if this goes to 0, we have trouble. Okay, so we can't use this equation if those two are equal. If they're equal, then we have to use this other equation. It's a little simpler, gets rid of that. It is Kd L naught T plus D naught, all that times e to the minus Kdt. Okay, so now we have a function, or two rather, that gives us the deficit, But we also want to know, when is that the maximum deficit? How do we find the critical time or critical distance that we're after? So first of all, we can relate the speed of the river to the distance it's traveling. Again, assuming this is pretty much a plug flow system. Obviously, from velocity is distance over time. So if we have time or if we have distance and we know the velocity, then we know the system. However, it would also be nice to be able to identify a function that'll give us the time where d is max. Okay, that is something we could do if we flip back to our plots where we were looking at the deficit, and we said it looked something like this, or that's the oxygen sag curve, and the deficit looks something like that. Well, we should be able to identify a condition where that's maximized, and sure enough, the book provides just that with this equation here. Tc being, this is the critical time, or critical point. That's what the C is standing for. So Tc would be 1 over Kr minus Kd times the natural log of Kr over Kd times 1 minus all this stuff, the d naught times Kr minus Kd divided by Kd L naught. Again, we kind of have an issue here. If we have equal rate constants, we're dividing by 0, so this one also will not work. I don't think we've got an alternate for this. So if we're in that circumstance, then we would need some other way to deal with it. All of this is assuming a constant velocity, or at least we will go ahead and assume that to keep things pretty simple, where our distance would be velocity times time, or time would be the distance over the velocity. Okay. So with that, basically what I'm telling you is we've got a couple big equations that we can use, and if we know something about the stream or river, its parameters, maybe that's something we could calculate from some geometry, then we can predict when and where and how bad is our oxygen deficit. Okay? So in this case, I hope that you recognize that, it is possible to integrate that equation, and we'll get this guy, but I'm not going to be asking you to integrate that on the exam, all right, or the homework. What I want you to know then is how to handle these equations, and when do we have to use the alternate equation. I'm going to give you both, so you'll have both on the formula sheet. All right, so with that, I want to give you some practice, give you some time to work on this one. I've got actually 2 here. So the first one, this is example 5.7 from our book, says the wastewater in a previous example is summarized in this table up here. It has a dissolved oxygen concentration of 2 milligrams per liter, a discharge rate of 1.1 cubic meters per second. The river that is receiving this water has a dissolved oxygen equal to 8.3 milligrams per liter, a flow rate of 8.7 cubic meters per second, and a temperature of 20 Celsius. Assuming complete and instantaneous mixing, estimate the initial dissolved oxygen deficit of the mixture of wastewater and river water just downstream of the discharge. Okay, I'm sorry, this is not a table of the water quality. This is a table of oxygen solubility according to temperature. So we've got 20 Celsius here, will correspond to 9.09. We'll go ahead and use that. Milligrams per liter of oxygen. Changes a little bit. This is including chloride, but this is fresh water, so this is going to be close enough. Okay, so take a few minutes, consider that, try to find this dissolved oxygen deficit initial. Right, that's going to be our D initial. I'll be back in a moment. So I went ahead and solved it, kind of giving you a couple more moments in case you were working on it. And for this first problem, we just have something a little bit straightforward. Can't get around, can't get away from these simple mass balances, right? You learn something fancy and then you just realize it's something very straightforward. So to begin the problem here, we need to know some of the basics, some of the foundational pieces. So as always, if you didn't start with drawing up the system and checking what really is what you're trying to answer, I'd encourage you to do that, right? This will show you that you have two streams mixing and you need the concentration of essentially one thing of the mixture. If you recall, that's exactly how we started our class, talking about any sort of mass balance. So we're doing a mass balance of these two streams mixing. We're doing it on the dissolved oxygen, and then we're going to do the small piece of extra to compare that to the dissolved oxygen at saturation to get our initial deficit. We'll notice that the problem says it's instantly mixed. So as soon as these two mix, then we have our DO initial, some mixture, DO mixture, and a Q mixed. So we can solve our Q mixed by adding the two together, and we can set it up from the starting point saying the dissolved oxygen, the deficit, DO deficit to begin with, would be the saturation minus whatever the mixture happens to be at. So that would be 9.09 from our table, that's milligrams per liter, minus whatever the dissolved oxygen of the combined streams is. So we find that, the DO of the mixture, based on our mass balance. What's going in, these two, is equal to what's going out, this one on the left. I drew it up a little differently, but you could write it as 0 equals Q in plus Q in the second one minus Q out, and separate it and go on from there, right? I just wrote it as what's coming out is equal to what's going in. Okay, so with that, we divide everything by QM and put in the numbers, and we'll get a mixed dissolved oxygen of 7.59 milligrams per liter and an initial deficit, therefore, of 1.5 milligrams per liter. What you'll notice, if you're looking closely, 8.3 milligrams per liter, that's what the river is at initially, before any wastewater added. That's not exactly our saturation point, but it's also not too far. So that would be pretty typical of a natural system. There's a bit of oxygen demand just from natural biology, but it should hopefully not be too far from. Okay, this makes sense? Any issues here? Okay, so then let's put the other equations, the fancy ones, to use. So the next step, we're going to follow that and say just below the point of some continuous discharge of pollution as it mixes with a river, the BOD is 10.9 milligrams per liter. The dissolved oxygen is 7.6 milligrams per liter. And the river and waste mixture has a temperature of 20 Celsius, a deoxygenation constant KD of 0.2 per day, an average flow speed of 0.3 meters per second, and an average depth of 3 meters. Bless you. In other words, we're just continuing from the previous problem, and now we have something about the KD and about the speed and depth of the river. So part A says find the time and distance downstream at which the oxygen deficit is at a maximum, and then B, find the minimum value of dissolved oxygen. Okay, I'm going to give you guys a little bit of time, maybe 10 to 15 minutes range to work on this. See if you can get it, work together if you'd like, and then I'll work through the solutions with you. Welcome to ask me questions as well. Mhm. One thing I didn't mention, by the way, um, this KR equation is kind of a weird one. This is going to give us a rate constant in per day with inputs of meters and seconds. Don't worry about it. The 3.9 here is kind of a fudge factor that's going to account for all the conversions. Okay, this is just empirical. We typically measure with meters per seconds. We typically measure the depth in meters. If you tried to look at the units, you've got meters to the 1/2 divided by seconds to the 1/2, all that divided by meters to the 1.5 power. It gets squirrely. Don't worry too much about it. Just take it for granted that this 3.9 includes all the conversions we need to make that convert into a per day. So the one time we're just going to mostly ignore the units. Just put in meters and seconds, and then we're good.
be mixed or right at the instant it's mixed?
So it has now been mixed.
It's like
So below would mean like downstream, meaning it has already been mixed.
Yeah, that's what I'm saying. Maybe I'm putting it in the calculator wrong.
Well, especially like using aluminum.
Oh.
I mean, that's just because I had.
I can't see the option. Okay, so you find the additional. We found this first one. And then you find TC. You gotta find TC, so you have something to plug in to find. And then plug TC into D.
I don't think I should. No, if I like, I would choose this.
That second equation. So
Like,
it's up here.
I would choose doing
That's the
this.
minus
I
K.
guess my code is.
You multiply by the velocity.
I've never that easy. I think the only thing that's most confusing is like all the different but like I feel like
He said.
That's maybe the tricky part of this is remembering the D and DO were not the same thing. If you get the D, it's the DO is whatever it's supposed to be minus the
Be a good choice.
Actually, 25 hours.
Oh, it's like here. Minus added up to 5 hours. Plus like
All right. How you feeling? Okay, so you probably saw I kind of began working through part A for you and ultimately did work through it. A couple things to note. You'd want to calculate that KR up front and compare that with KD to make sure that they are not the same. If they are the same, we have to choose this equation, but they're not, so we do not use that equation, which means we're going to use this equation, right? So given that we're going to use that one, well, that's good also because we couldn't really use the TC equation if those were the same also. So perhaps we couldn't even do the question if that was the case. Anyway, that's probably good to go ahead and get taken care of, figure out those values. Should be, our KR should come out to 0.41 per day. Most of the rest of the parameters were given. It was just a matter of understanding what it was giving you. So the river just below this mix, we were told that the BOD is 10.9 milligrams per liter, and we can treat that as our ultimate BOD, the initial amount that's there. Okay, so that will be our L naught. That's going to go into our equation right here. The other piece would be the deficit, which is essentially the type of thing we calculated in the previous problem. In that case, it was 1.5 milligrams per liter. Based on those calculations, effectively, if we were to look closely, that's probably the same thing, 1.49, that was given in the sense of our problem setup here was saying, draw that a little better, was saying, okay, our mixture has 7.6 milligrams per liter. Our saturation value is 9.09. So that gives us an initial deficit of 1.49. So with that, we can put in all of our numbers if we do that correctly, which is not necessarily a trivial task with all these parentheses and everything, we should end up with a critical time of 2.67 days. We can get from there to the distance, but it'll be nice to convert because we have our velocity in seconds. We ought to convert that up to per day, and then maybe from meters to kilometers because we have a lot of them, and that'll end up giving us 69.3 kilometers with 2.67 days elapsed after our discharge. So it's actually quite some time, right? That's a fair ways down river. I guess, 50 miles or something like that, almost. That's a little ways away. Takes 2.5 days before we really get the trouble spot. So then part B says, okay, well, what is the minimum value of DO? So that means we probably need to know the maximum value of the deficit. So the deficit at time critical, and then calculate from there to get our minimum. So what we can do is find exactly that. We're going to use our deficit equation now, this guy, in order to find that. So we can simply say our deficit should be this equation, and we're going to use the time at that critical point, the 2.67 days. So we'll use this equation. Get this out of my way. Okay. And in here, we'll just insert the time that we solved for in each place we have t, and we can find a deficit. Bring my solutions back. Should be 3.1 milligrams per liter. And that's the amount missing, but the question was what is the minimum value of DO? So if we say DO minimum, or at the critical point, would be the 9.09. I'm just going to call it 9.1 minus 3.1 will then give us essentially 6 milligrams per liter. Okay, technically, 5.99 if I did that very thoroughly, but that'll be good enough for now. So 6 milligrams per liter is the amount remaining, and as far as I know, that's usually pretty protective of most fish and wildlife. There might be certain species that would be sensitive, but perhaps not in this. That would be a little atypical, I think. Okay, so with that, I think I might have one more problem for us to work on this topic next time, or maybe I'm thinking of the homework. Probably thinking of the homework problem that you have that's related. So we'll cover that after Thanksgiving when we do that exam review. I'll send an email, but tomorrow we'll do a virtual, not here, exam recap for exam 2. Homework is posted, and after the break, we will have kind of one lecture, one exam review session, and then it'll be off to finals. So in case I don't see you, have a happy Thanksgiving, and enjoy the weekend.